Hello and welcome to today's lecture on medium access control. This is the third lecture on this topic. In the first lecture, we discussed about the contention based medium access control protocols like Aloha, CSMA, CSMA CD. In the second lecture, we have discussed about the collision free protocols, where we have discussed the token ring and other protocols like round robin protocols and reservation protocols. In this lecture, we shall discuss about another very important approach that is based on channelization. So, here is the outline of the lecture. First, I shall discuss about the basic concepts of channelization, and I shall give a analogy based on cocktail party theory, which gives you some idea how the channelization medium access control techniques work. Then we shall discuss the three important types of channelization based medium access control techniques, such as frequency division multiple access FDMA, then time division multiple access TDMA, then code division multiple access CDMA. And this code division multiple access CDMA is very complex, and we shall discuss how it is used, and particularly different aspects of it, like the transmitter and receiver, how the multiplexing and remultiplexing is done, then how the chip sequences which is used in CDMA is used here, and how the chip sequences are generated with the help of the Walsh table. And on completion of this lecture, the students will be able to explain the basic idea of channelization. They will be able to explain FDMA technique. They will be able to explain the TDMA technique, time division multiple access technique, and understand the basic concepts of CDMA, and they will be able to explain how multiplexing and demultiplexing occurs in CDMA, and they will be able to explain the orthogonal property of the chip sequences which are used in CDMA. And finally, they will be able to explain how chip sequences are generated with the help of Walsh table. So, here is the basic overview of the medium access control techniques. As I mentioned in the first lecture, I discussed about the random access type protocols like Aloha, CDMA and CDMA CD. And again, the Aloha has two different varieties, pure Aloha and slotted Aloha. And in the last lecture, we have discussed about the that collision free protocols, where the collision is avoided, and there are a number of techniques, which one is known as CSMA CA, collision carrier sense multiple access with collision avoidance. Then there are two other basic approaches like round robin, where you have got two techniques, polling and token passing, we have discussed in detail. Then the reservation based protocol, having two distinct categories of protocols which are based on centralized scheme and distributed scheme. All these things we have discussed in the last lecture, and in this lecture, as I mentioned, we shall discuss about the channelization approach based on FDMA, TDMA and CDMA. Let us first try to understand what do we really mean by channelization technique. It is essentially a multiple access method in which the available bandwidth of a link is shared in time, frequency or using code. So, there are three basic approaches. The bandwidth is shared in time, in frequency or using code by a number of stations. So, these three alternatives, that means sharing by in time, sharing in frequency, sharing using code, has led to three different approaches like FDMA, where the bandwidth is divided into separate frequency bands, and then different frequency bands are used by different stations. Then TDMA, where the bandwidth is time shared, that means at different instants of time, different users the stations uses the medium. On the other hand, in CDMA, the data from all stations are transmitted simultaneously and are separated based on coding theory. So, here we find that it is neither frequency shared or time shared, but here it is based on coding theory. So, all are transmitting simultaneously in terms of frequency and time, and being separated by using coding theory. It can be best explained, the three basic approaches can be best explained with the help of a very simple cocktail party theory. Suppose a cocktail party is going on, say banquet dinner of a conference is going on, and it is going on in a big area, and there are three possible alternatives. In one case, when all the people group in widely separated areas and talk within each group, that means in this case normally we have seen different people having different kinds of interest, groups in different locations, different areas of the cocktail party area, I mean where the cocktail party is going on. Then they talk among themselves, and when all the people group in widely separated areas and talk within each group, this is essentially we may call it FDMA. That means as if we have assigned different frequency bands to each of these groups, and each of these groups are talking using that different frequency bands. So, this is your FDMA approach. Another alternative is when all the people are in the middle of the room, but they take turn in speaking. In the second situation, some very important event is going on, and all the people have gathered at a central place, and each of them is taking turn in talking. So, in this case it is equivalent to TDMA or time division multiple access. So, here the basic approach is that it is in terms of time the sharing is taking place. Now, the third approach is very interesting, when all the people are in the middle of the room, but different pairs speak in different languages. So, it is not unusual that in an international conference, when the banquet dinner is going on, people from different countries will arrive there, and obviously when they group together they may be speaking in different languages. Let us assume that all of them had gathered near the central area, but small groups are talking in different languages. A group is talking in English, a group is talking in French, a group is talking in German, another group is talking in maybe Bengali, another is Hindi. So, you can see each of the groups are talking simultaneously. Since they are speaking different languages, the person who is talking in the group who are talking in English, although they are hearing the voices spoken in say Hindi or French or German, that will not interfere with their discussion. So, here simultaneously all of them are talking, but they are not interfering with each other because they are talking in different languages. So, this is equivalent to CDMA or code diffusion multiple access. So, here we shall see how all the people can talk simultaneously at the same time. They will not interfere with each other, or each of them can separate what they are talking within the group. So, this is the cocktail party theory, the analogy of the three channelization approaches based on cocktail party theory. Now, let us first focus on the frequency division multiplexing. So, in frequency division multiplexing, we have already seen we have got a number of sources, and say you have got say n sources as shown here. Each of them is sending some data, and they are the signals coming from each of the sources are modulated by using different frequencies, carrier frequencies f1, f2 and fn, and as a consequence they are creating signals in different frequency bands, and they are combined together, and all the composite signal, as you can see here, with center frequencies f1, which is the carrier frequency of the modulator 1, and f2, and as you can see, each of the signals coming from each of the sources are now channelized in terms of frequencies. That is why it is called frequency division multiplexing. So, here the overall bandwidth is divided into separate frequency band, and each of the channel is using one of the channels to transmit. So, this is how frequency division multiplexing occurs. Now, we already know that the number of you have to use guard bands in between the frequency bands of a pair of adjacent channels. So, channel 1 and channel 2, these two are adjacent channels. So, their carrier frequencies are FC1 and FC2. You have to use some guard band between the two, so that they are separated by strips of unused bandwidth to prevent inter-channel crosstalk. So, as you know, whenever you perform that frequency modulation, the bandwidth increases, and as you have to separate you have to overcome the crosstalk. So, inter-channel crosstalk has to be avoided, and to do that guard bands are used. So, whenever you have got a number of channels, so this particular equation shows what is the number of channels that can be used. That means, number of channels that can be used, n is equal to Bt minus 2 Bt. Bt is the total bandwidth available, and that is being divided into a number of channels. The bandwidth allocated to each channel is here, and Bt minus the total bandwidth minus 2 Bt by Bc. So, we see, so this is how we get the total number of channels that can be used, that can the total number of channels that is possible in case of frequency division multiplexing. Now, you may be asking, what is the difference between frequency division multiplexing and frequency division multiple access? So, as you can see here, as you can see, the signals sent by different channels have been shown in terms of in a 3-dimensional graph, where the 3 dimensions are time, frequency and code. So, as you can see, the signals coming from different channels are only varying in terms of frequency here. However, in case of bursty traffic, the efficiency is improved in FDMA by using a dynamic sharing technique to access a particular frequency band. Now, normally for each of these channels, a frequency is statically allocated, but if the traffic is bursty, that means all the channels do not have data to send all the time. In such a case, what can happen? There can be underutilization of the channels, because a channel is statically or permanently allocated to a particular station or user. So, in such a case, if the traffic is bursty, that particular channel may not be used. What can be done to improve the utilization? So, instead of statically allocating the band, allocating a particular channel to a particular station, the channels can be assigned on demand. That means, depending on the requirement of different stations or users, a single channel can be allocated to different stations or users. So, that makes it FDMA, frequency division multiple access. That means, not only the overall bandwidth is divided into a number of channels, each channel can be allocated to a number of stations or users. So, if you have got n channels, now since each channel can be shared by more than one user, the total number of stations that can be provided service can be greater than n. If it is statically allocated, then the total number of stations that can be that can use this service is equal to n. However, since this is allocated or assigned dynamically on demand, the total number of stations can be larger than the number of channels. So, obviously, this is possible only when the traffic is bursty in nature. If the traffic is streamed, that means continuously sent, then of course, it is not it cannot be done. So, that's how the frequency division multiplexing That is the difference between frequency division multiplexing and frequency division multiple access. In case of frequency division multiple access, as we have seen, each channel can be used by different users based on the assignment done on demand. So, this is your frequency division multiple access. Now, let us focus on the time division multiplexing. As you know, the incoming data from each source are briefly buffered. We have already discussed the time division multiplexing at length, and we have seen that each buffer is typically either 1 bit or a character in length. The buffers are scanned sequentially to form a composite data stream, and the scan operation is sufficiently rapid. So, scanning is done very fast, so that each buffer is emptied before more data can arrive. So, this basic approach we have already discussed, and here it is shown how it is being done. So, here are the buffers coming from different sources, and this here you have got some kind of switch. So, it is first it is shown between the connection is established between S1 and this output, then S2, then in this way it takes turn up to Sn, but it is done very fast, and some kind of framing is done, and composite signal, as you can see, is framed where you have got data from S1, S2 up to Sn, then it is repeated, again another frame comes S1, S2, Sn. Of course, the composite data rate must be at least, so here will be at least equal to the sum of the individual data rates. So, if you sum up the individual data rates, say you have got n channels, n into say data rate is b, then this scanning has to be n into b. That means, here the rate will be at least the n times of the individual data rates when you have got n stations or channels. Then the composite signal can be transmitted along with synchronization bit. Just like the guard bands we are used in frequency division multiplexing, and guard band is essentially some kind of overhead bits, Similarly, here the synchronization bits are overhead bits, as we have seen in case of time division multiplexing. And here also the problem arises if the stations do not have data all the time. So, here for example, the first frame is filled up because there is data A, B, C, D. On the other hand, in the second frame there is data from A, B, C, but there is no data from D. So, it goes empty. Similarly, in frame 3 A, B, C, D, you can see that C, D has no data to send, and this is the transmitter end, and in the synchronous manner it is received at the other end, as you can see, and A, B, B, C, C and D, D are collected. But as you know that synchronous time division multiplexing leads to underutilization of the channel if the data is bursty in nature, and that is why we developed another approach which is known as asynchronous time division multiplexing, or ATM. Asynchronous time division multiplexing, where instead of allocating a fixed slot for each of the channels, the slots can be different. But in TDMA it is done in a little different way. So, as you can see here, the frequency and code remains same for each of the channels, however, the time slots are varying, and in this case the number of channels is equal to n, and where m is the number of bits for each of the stations multiplied by B total, that is the total bandwidth available, minus 2 into the guard bandwidth by BC, that is the bandwidth of each of the channels. So, you have got separate channels. Now, just like the case of TDS, that frequency division multiplexing, here also it is possible to assign the slots to different stations or users dynamically. So, channel allocation can be done dynamically. Whenever we do that, for example, this particular channel can be statically allocated to a single station or user. In that case, we call it time division multiplexing. On the other hand, if it is done dynamically and on based on demand, then we call it time division multiple access. That means a particular channel can be shared by a number of stations or user. So, that is your time division multiplexing. So, not only we are sending, you are dividing into different time slots, but each of these time slots can be shared by more than one station or user. So, that is essentially the TDMA or time division multiple access. So, we have discussed the two basic channelization approaches. Now, let us focus on the other one, the most complex one, the code division multiple access, CDMA, code division multiple access. So, in CDMA, as you can see that it is neither divided in terms of time nor divided in terms of frequency. Each of the channels occupy the same frequency and time simultaneously. However, they are separated in terms of codes. So, you have got channel 1, channel 2 and channel n having using different codes, and how exactly it is being done by using different codes will be explained very soon. So, here are the basic differences between TDMA, FDMA with CDMA. So, in TDMA and FDMA, the transmissions from different stations are clearly separated either in either time or frequency, as you have seen. So, they are sent in different time slots, or from different users different frequencies are used. But in CDMA, the transmission from different stations occupy the entire frequency band at the same time, as you have seen in this particular diagram. So, you can see all of them, all the channels are transmitted in the same time and using the same frequency bands. Now, it is possible to have multiple simultaneous transmissions separated by coding theory. So, we have to use some kind of coding theory, so that it is possible to have multiple simultaneous transmissions and which can be separated by coding theory. What is being done? Each bit is assigned a unique m bit code or chip sequence. That is the basic idea. That means, each bit of a channel is assigned a unique m bit code or chip sequence. As you can see, how the multiplexing is being done is shown here. So, here the binary data is coming from four different sources, that is your say station 1, station 2, station 3, station 4. So, station 1 0 is coming, station 2 1 is coming, from station 3 0 is coming, from station 4 1 is coming. Now, for pedagogical purposes, this 0 is represented by -1. On the other hand, 1 is represented by +1. So, you can see here 0 is represented by -1 and 1 is represented by +1 for pedagogical purposes. Now, each of these stations is having a unique chip sequence. So, this chip sequence for channel 1 is +1, +1, +1, +1, essentially it is 1 1 1 1. On the other hand, for station 2 it is +1, -1, +1, -1. It is different from the chip sequence of channel 1, and then for channel 3 the chip sequence is +1, +1, -1, -1. Again it is different either from station 2 and station 1. Then finally, you have got the chip sequence for station 4, which is +1, -1, -1, +1. As you can see, all these 4 chip sequences are unique. Each of them is different from the other 3, and then this binary input is multiplied with the chip sequences. So, plus and minus leads to -1 and minus. So, whenever it is multiplied with minus, +1, +1, +1, +1, +1 becomes -1, -1, -1 and -1. On the other hand, this is for channel 2, it is multiplied with +1, it becomes +1, it remains same. So, +1, minus 1, plus 1 and minus 1, it remains same. So, then minus 1 when it is this is multiplied, it becomes minus plus 1 minus 1 minus 1 chip sequence becomes minus 1 plus 1, and from station 4 it is multiplied with plus 1, that is because of the binary data is 1. So, it becomes plus 1 minus 1 plus 1 becomes plus 1 minus 1 plus 1. Now, these are added bit by bit. So, here you see plus 1 plus minus 1 plus 1 minus 1 plus 1 becomes 0. For the second bit minus 1 becomes minus 4, you have to add to alt 4, then minus 1 plus 1 minus plus 1 minus 1 becomes 0, and minus 1 plus 1 becomes 0. So, the composite data, that composite signals is corresponds to that 0 minus 4 0 0. This can be sent over the medium. So, this can be sent over the medium. So, this is sent and it is being received at the other end. So, here it comes from the medium. So, after it is received, you see the same chip sequences which were used for different channels are used for demultiplexing. So, it is multiplied with the same chip sequences. So, after multiplying with chip sequences, you see this is 0 minus 4 0 0, it becomes 0 minus 4 0 0, and this is 0 minus 4 0 0 multiplied with minus plus 1 minus 1 plus 1 minus 1 becomes 0 plus 4 0 0, and similarly 0 minus 4 0 0 multiplied with plus 1 minus 1 becomes 0 minus 4 0 0. Similarly, 0 minus 4 0 0 multiplied with plus 1 minus 1 plus 1, which is the chip sequence of channel 4, it becomes 0 plus 4 0 0. Now, if you add together, you have to perform the addition. Here you are doing addition. So, if you add, then you get minus 4. Here if you add all the 4, you get plus 4. Here if you add, it becomes minus 4. If you add plus 0 plus 4 0 0, you get plus 4. Then you divide by 4 because you have got the total number of channels 4. Then you get minus 1 here, plus 1 here, minus 1 here, plus 1 here. So, after dividing by 4, you get plus 1 minus 1 plus 1 minus 1 plus 1. So, as you know, minus 1 is nothing but 0, plus 1 is nothing but 1. So, whatever was transmitted, that 0 1 0 1, as you have seen, that 0 1 0 1 is now recovered. So, all of them were sent simultaneously, and the demultiplexer, they can be separated out again by multiplexing with chip sequences. So, in practice, this is being done in this way. So, the binary information comes here, that 0 or 1, that is being multiplied with the help of that random sequence. Actually, this is a, if the R is the bit rate of the data, then the spreading factor is selected such that it occupies the entire frequency band of the medium. That means, the number of bits in this chip sequence is chosen such that it occupies the entire bandwidth of the channel. So, it can be 8, it can be 16, or it can be 128, depending on the bandwidth of the medium. So, you see the signal that comes out is it becomes m times, which is the number of bits in the chip sequence, the data rate of the medium. So, after multiplying, this is the signal that is being generated, and now you can perform digital modulation like that QAM, QPSK, this kind of modulation you can do. Then you can transmit by using a antenna. So, this is how the transmission is performed, and as you can see, the bandwidth of the bandwidth here is 8 times the bandwidth of each of the channels. Now, at the receiving end, the all the stations, signals from all the transmitters are being received. So, signals from all the transmitters are being received by this antenna, then the composite signal is multiplied with the digital multiplier, digital demodulator. Again, this digital demodulator means that that decoding is being performed, as you have seen in the case of digital modulation was done. So, demodulation is being performed, and after demodulation we get that composite signal, and that is being multiplied with that unique pseudo random binary sequence, and after multiplying the binary pseudo random binary same pseudo random binary sequence, we get back the signal. Of course, it will have some noise because of interference and other problems, but you get back the binary information. Now, you may be asking, how do you generate these chip sequences? This is being done by using linear feedback shift register. You may recall that cyclic redundancy code when we use for error detection by using cyclic redundancy code, to generate that cyclic redundancy code and also to check it, we use some linear feedback shift register to generate a random sequence. So, that kind of linear feedback shift register can also be used here to generate those unique pseudo random binary sequences. So, unique pseudo random binary sequence is used in transmitter as well as in receiver. Now, it is necessary, of course, there is one problem here. We have assumed that the signals coming from different stations have the equal strength. That means, it is necessary to this necessitates a power control mechanism at each transmitter to overcome the near far problem. Essentially, the near far problem arises because, if there is a receiver which is receiving signal from a number of transmitters, and depending on the distance, if it is very near, then the signal strength coming from that signal will be very high, and the signal strength from other signals will be low. And as a result, the signals coming from the if the signal strength is very low, that will be ignored. So, that will be considered as 0, and if the signal strengths are not equal, then the noise will increase, here interference will increase. In other words, the summation and then subsequent detection is based on the assumption that they are of equal amplitude. So, that is why some kind of power control mechanism is used as each transmitter to overcome the near far problem, as it is used in cellular telephone network. We shall discuss about it later on. Now, let us discuss more about the chip sequences. As I mentioned, each station is assigned a unique m bit code or chip sequence. Obviously, these are not randomly chosen sequences. You do not generate them in an arbitrary manner. If you generate them in an arbitrary manner, then that property of that the property of orthogonality will not be satisfied. So, you have to satisfy the orthogonal property. I shall explain what does it mean. Let us use the symbol SI to indicate the m bit vector for station I, and SI bar is the complement of SI. Now, all the chip sequences are pairwise orthogonal, that is, the normalized inner product of any two distinct codes will be 0. So, for example, the S1, the code one code is +1 -1, this is your -1 +1 -1, and S2 is +1 +1 -1 and -1. If you take the inner product of these two, that means you multiply +1 with +1, you get +1, then +1 with -1, you get -1. Then if you multiply with -1 with +1, you get -1, then -1 and -1, if you multiply, you get +1. So, if you add them, this is the inner product. If you take the summation of these, then you will get 0. That means, if you choose any two distinct codes, it will be 0. That means, S1 into S2 it is 0, S1 into S3 will be 0, S1 into S4 will be 0, and on the other hand, if you multiply the same code S1 into S1, if you do the multiplication, +1 with +1 becomes +1, +1 with -1 will become +1, then minus 1 with minus 1 will become plus 1, minus plus 1 with plus 1 will become plus 1. If you add them, it becomes 4, and if you divide it by the number of bits, you get 1. So, we find that if it is if you multiply S1 with S1, that means the same codes, same chip sequences, you get 1. On the other hand, if you multiply with the complement, you get again 0. That means, if a code S1 or Si is multiplied with Sj, where I is not equal to j, then it is 0. And also, whenever it is multiplied with its complement, also it is 0. So, this is the orthogonality property to be satisfied by the chip sequences. Only then the multiplexing and demultiplexing is possible. In other words, simultaneous transmission and subsequent recovery at the receiving end is possible only when this orthogonal property is satisfied. So, as I mentioned, the orthogonal property allows parallel transmission and subsequent recovery at the receiving end, and I have already explained how exactly it is being done with the help of these two diagrams. So, here you are doing the multiplexing, and as you can see, the chip sequences satisfy the orthogonal property. Then you can sum them together, then you can transmit, and at the receiving end you can separate out. So, this is how the chip sequences are to be designed. Now, now let us take up several examples. Suppose the S1, S2, S3 and S4 are assigned to channel 1 A, B, C and D. Now, let us assume at a particular instant channel say A, B, C, D. So, let us assume A is not transmitting, D is not transmitting, B is transmitting 0, C is transmitting 1. And another example, say A is transmitting, B is not transmitting, C is transmitting 0 and D is not transmitting. Third example is C is not transmitting, A is transmitting 1, B is transmitting 0, C is not transmitting and D is not transmitting. That is this is transmitting. Now, what will be the composite signal in the 4 cases? So, for B you have to multiply with this, that minus 1. So, it becomes minus 1, minus 1, plus 1, plus 1. Then you have to add with that, that is for C it is plus 1, plus 1, minus 1, plus 1. So, that is your plus 1, plus 1, minus 1, minus 1. So, if you add them, it becomes, this is your 0, 0, 0, sorry, this is 0 and this is minus 1, minus 1, minus 1. So, it becomes plus 1, plus 1, and here it is, I think there is something wrong in this. These two cannot be same, S1, S2, S3 and S4. Let us look at the S3 code. S3 is plus 1, plus 1, minus 1, minus 1. That was plus 1, minus 1, plus 1, minus 1. So, S1 is, so this is these codes are not proper. So, let me take up separate codes, that is your S1 is assigned to A, that is your plus 1, plus 1, plus 1, plus 1. Then S2 is assigned to B, that is your plus 1, minus 1, plus 1, minus 1. So, in this way, if you assign and if you perform that multiplication and addition, you will see whenever you are transmitting A and you are transmitting C, or you are transmitting the A bar and C, or if other stations are not transmitting, even in that case also it will work. That what I am trying to tell, whenever you have got some stations not sending, even then it will work. That means, in this case if some station is not sending data, say this is not here, that means B is not sending, this is dash. So in that case it will be 0 0 0 0, even then it will work. That means if it is 0 0 0 0 and if you do the summation, you will find still at the receiving end you will be able to detect by proper addition. So later on we shall take some more examples to illustrate how that kind of this example. I think these codes are not proper, these are not orthogonal, and if we take orthogonal codes and take some stations transmitting, some stations not transmitting, still it will work. That means you can say you have got A, B, C, D. It is possible that two stations are not transmitting, one is sending 0, another is sending 0, one is another sending 1, and all possible combinations are possible. Even in this situation, it will be possible to multiplex and demultiplex at the other end. Now, you may be asking how the chip sequences are generated. What is the technique that is being used to generate the chip sequences? They have to be pairwise orthogonal. That can be done by using Wallace table and in an interactive manner. That means Wallace table can be used to generate orthogonal sequences in an orthogonal interactive manner. How? The W1 is plus 1, as you can see, it is a one dimensional matrix, and W2 is a two dimensional matrix. I mean two dimensional matrix with 4 entries. Here you have got only one entry. So 2n, 1, 2n, 4n can be generated. 1, 2, W1, W2, W4 can be generated in this manner. That if W1 is 1, W1 if Wn, if Wn can be used to generate W2n. So how do you generate? W2n is generated from Wn by putting Wn, Wn, Wn and Wn bar here to get W2n. For example, W1 is plus 1 and W2 is, here we have substituted W1, W1, W1 and W1 bar. That means plus 1, plus 1, plus 1 and minus 1. Then W4 can be generated from W2. This is how this is being done. Let me show here. So W4 is equal to, so you have to put this matrix, that means plus 1, plus 1, plus 1, minus 1. Then here also you have to put plus 1, plus 1, plus 1, minus 1. Here also you have to put Wn. So plus 1, plus 1, plus 1, minus 1. Now here you have to put the complement of that. Complement is minus 1, minus 1, minus 1, plus 1. So minus 1, minus 1, minus 1, plus 1. This is exactly what you have got. Similarly, W8 can be generated. W8 will be equal to W4, 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 W4 bar. So in this way you can generate the next bit sequences in an iterative manner. So if the table for n sequences is known, the table for 2n sequences can be created, and it can be proved that these sequences satisfy the orthogonal property. So this can be used for the purpose of CDMA, and also the codes can be generated very easily, and these sequences can be also generated by using that linear feedback shift register, as I have already told. So we have seen how the chip sequences can be generated in a very convenient manner by using Wallace table. So friends, we have discussed various techniques, various medium access control techniques in 3 lectures. First lecture, as I mentioned, we discussed about the random techniques, Aloha, CSMA, CSMA CD, and in the next lecture was collision free protocols, and where we have discussed carrier sense multiplexes with carrier avoidance, then round robin and reservation techniques. And we have in the today's lecture we have discussed FDMA, TDMA and CDMA, and here we have seen the signals can be transmitted by in 3 different ways, by using frequency in terms of time, frequency and code division multiplexing. Now, these techniques, medium access control techniques, have many real life applications. We have in the next few lectures we shall discuss about the applications of these medium access control techniques used in broadcast communication, and 3 important applications we shall consider. First one is the local area networks, second one is the satellite networks, third is the cellular telephone networks. In local area networks we shall consider 3 lectures. First one will be based on the IEEE 802 LANs, and you will see there we have used CSMA CD and token passing protocol. These 2 protocols are being used in IEEE 802 LANs, which I shall discuss in the next lecture. We shall also discuss the high speed LANs, where these medium access control techniques are used in high speed LANs based on that CSMA CD, which are essentially fast Ethernet, gigabit Ethernet, and also FDDI, fiber distributed digital interface, which uses token passing protocol. So, in high speed LANs both CSMA CD and token passing protocols are used, and there will be another local area networks, that is your wireless LAN, where we shall find the use of that CSMA CA protocol. So, CSMA CA protocol will be used in wireless LAN. Then we shall consider the satellite networks, and satellite networks we shall see there is use of FDMA and TDMA, time division multiplexes and time division multiplexes and frequency division multiplexes, and primarily reservation techniques are used in these applications. And finally, we shall consider another lecture where we shall consider the use of TDMA, the cellular telephone network, where the time division multiplexes, frequency division multiplexes and code division multiplexes are used, as we shall see different standards like GSM and CDMA, where these channelization approach of medium access control technique is used, and we shall see how this TDMA, FDMA are used, and also how CDMA is used in implementing cellular telephone networks. So, in the next 3 lectures we shall discuss the applications of the applications of these medium access control techniques, and we shall see how these medium access control techniques are used. Now, it is time to give you the review questions. First question is, in what way frequency division multiplexing differs from FDMA? So, we have already discussed the FDM frequency division multiplexing earlier In this lecture we have discussed frequency division multiple access. So, the first question is based on that, in what way FDM differs from FDMA. Second question is, in what way CDMA differs from FDMA. So, third question is, what happens when multiple signals collide in CDMA. We have seen that in CDMA the various transmissions coming from different sources are done simultaneously. So, whenever collision occurs, what happens in case of CDMA, that is the question, third question. Fourth question is, what is an inner product in the context of CDMA. Fifth question is, compare and contrast FDMA, TDMA and CDMA techniques which has been discussed in this lecture. So, these are the 5 questions to be answered in the next lecture. Now, let us consider the answer to the questions of lecture number 26. First question was, what are the advantages of collision free protocols over random access protocols? Answer is, in random access protocols there is loss of bandwidth due to collisions and retransmissions. So, we have seen that in random access protocols based on Aloha, CSMA and CSMA CD, there are collisions, and whenever there are collisions, as you know, it is necessary to do retransmissions. So, and as you know, whenever the traffic increases, the number of collisions keeps on increasing, and that reduces the throughput, and that is the drawback of these random access protocols. On the other hand, in collision free protocols there is no loss of bandwidth as there are no collisions. We have seen that in CSMA collision carrier sense multiple access, collision avoidance or say polling, or in token passing, or in say based on reservation, collision is completely avoided, and as a result there is no loss of bandwidth due to collisions. So, that is the advantage of this these protocols. So, collision is completely avoided, there is no loss of bandwidth, and as a consequence the collision free protocols are advantageous, particularly when the load is high, traffic load is high. Then comes the second question. Second question was, how does CSMA CD differs from CSMA CA? In CSMA CD, collision occurs as traffic increases in the network. Although binary exponential backup algorithm is used to minimize the number of collisions, efficiency drops with increased traffic. We have seen that in case of CSMA CD, whenever collisions occur, the by using that binary exponential backup, the backup time, average backup time is doubled. So, that minimizes the number of collisions, but in spite of that, as the traffic load increases, the throughput decreases, as we have seen, particularly when the load is high, like this, the traffic in this particular region, and the number of collisions occur, the loss due to number of collisions is more, and as a result the throughput decreases. On the other hand, collision is avoided in CSMA using 4-way handshaking protocol. As you have seen, 4-way handshaking protocol is used by using that request to send, clear to send, and by listening this clear to send, the other stations backs off, do not send their data, and this way the collision is avoided, and this is particularly suitable in wireless environment where collision detection is difficult. Third question was, compare and contrast CSMA CD and token passing protocols. The token ring is the least sensitive to workload. We have seen that in token ring, although when the station the network is lightly loaded, the the overhead is high, but it is less sensitive to workload. As the load increases, the throughput does not decrease. On the other hand, CSMA CD offers the shortest delay under light load conditions, but it is most sensitive to variations of load. That means, when the load increases in CSMA CD, we know that that delay increases significantly, particularly when the load is heavy. Another important difference is that token ring is suitable for real time traffic because the delay is deterministic. You know what is the worst case time? Deterministic. But in CSMA CD it is not deterministic. How long time it will take, it is not known. As a consequence, the in case of CSMA CD, some packets may take very long time to deliver, and there is a possibility that some unfortunate packet will not be delivered, because in binary exponential backup algorithm, after 15 collisions a packet is dropped. So, it is not guaranteed that a particular packet will be delivered. So, that is why, because of the deterministic nature of token ring, it is suitable for real time traffic. On the other hand, for non real time traffic, when the load is lightly loaded condition, CSMA CD protocol is better. Fourth question was, why CSMA CD or token passing medium access control protocols cannot be used in satellite communication? As I have told, long round trip propagation delay in satellite communication makes it unsuitable for both collision detection based and round robin based protocols. As we know that delay here is about quarter of a second. So, if collision is detected by a ground station, that has happened quarter of a second earlier. In other words, that value of A, which is the ratio of the propagation time by transmission time, is very high. As a result, the CSMA CD based protocol is not suitable. Similarly, round robin based protocols are not also suitable because it takes very long time to do polling or to pass the token. As a result, these protocols cannot be used here. The final question was, compare the distributed and centralized reservation protocols. As I have mentioned, distributed schemes suffer from the disadvantage of higher processing burden of on each station. So, each station has the responsibility to perform that medium access control. So, because it is done in a distributed manner. So, the processing requirement is high on the stations. On the other hand, in distributed schemes, moreover, the distributed schemes are vulnerable to loss of synchronization, because you know that synchronization is very much essential, and in a distributed schemes it cannot be done, which can be very easily achieved in centralized schemes, and that is why centralized schemes has some advantage. However, distributed scheme is preferred, because if the centralized station fails, then the medium access control cannot be done. So, it is much more reliable. So, friends, in this lecture we have discussed the channelization scheme of medium access control technique, which concludes our discussion on medium access control technique. And as I have mentioned, in the next 3 lectures we shall discuss the applications of the various medium access control techniques we have discussed in 3 lectures. Thank you.